Pencils, calculators. I've got 10 or 11 example problems. So it's technically not anything new, but a few of them we haven't tried problems like this yet. So I guess it is new, but it's still the same overall topic. Simplifying radicals and then rational exponents. Morning, Delaney. Any questions at all before we get started, please? Okay. As always, jump in, interrupt me, turn on that mic. It's okay. I want you to if you have any questions. Real quick before we do any our problems for today, I wanted to just go over required homework so far. I know things got a little confusing, and I apologize for that. Last week, we had our 6 questions from the second day of class. So if you look on my YouTube channel, which I can't believe I have a YouTube channel now, but just for math, it's this video, Properties of Exponents Part 1. So at the end of that lesson are 6 questions that you all should have done on paper. A lot of you did, and you sent it to me, so thank you for people who did it already. But that is required homework, okay? It wasn't like a mastery test. It was just 6 questions on paper. And then we did do last week also mastery test number 1. And that one's called Properties of Exponents. So that's required homework. If you haven't done it, I'd like you to try doing that today. And if you need help on it, please let me know. Try it out on your own first, though. And that's actually it, because then things got a little weird on Monday and Tuesday of this week. And so the truth is, some people did Monday's homework, which was the next mastery test, but only one person has passed it so far that I noticed. So I'm going to make that one extra credit. So let me add that in here. Mastery test number 2. If you did it, I'm going to count that as extra credit at this point. And if anyone else would like to try it, that's extra credit. So please go for it, but I'm not going to require it as of now, okay? You can still do it if you want to. And let's see. I'll keep that up. Any other questions about the required homework so far, please? Comments, concerns? It's really just those 2 things. I am going to have some problems to do on paper today at the end of the lesson. No questions. Okay. So here's my plan for today. We're going to, again, like yesterday, review how to simplify radicals. And then we're going to do some more fraction exponent problems. Remember, these are related. These are kind of like the same topic. But I looked at all of our skills, and I wanted to just kind of start at the beginning, so to speak, and just build up slowly to the harder problems. So that's what today is going to be, is more practice. I really appreciated and enjoyed how many people were answering yesterday, were trying the problems with me, were giving me feedback. So I want to see if we can do that again today with more radical problems and then fraction exponents. All right, it's 10:07 on my clock. Let's get started. Oh, and that's just a reminder. Take notes, please. I may or may not be asking to see your notes at the end, so take them so that way you have them for yourself and you get credit if I ask to see them. And then ask questions. Don't just rely on someone else to ask. It's okay. I want to hear from you specifically. And it's okay to answer questions. So obviously, I'll be putting out the call to, does anyone have a guess or an idea on how to do this problem, or did you get an answer? I want to hear from you if you tried it out. And just a reminder, I'll be doing 6 questions at the end of today's lesson. So be ready for that, so you can take a picture of them or write them down so you can do that homework. Okay, here we go. So let's start off right away with simplifying radicals. And I've got a nice small number to start with. So square root of 20. So you may be thinking, okay, I'm just going to plug that in my calculator. There's nothing wrong with that. It just doesn't give you an exact, precise answer. If you try it in your calculator, square root of 20, it comes out to a decimal 4.472, and it goes on forever. What we want is the precise algebraic answer. So it's going to be something times square root of something. How do we find this? Well, we saw on Monday and yesterday the way to start simplifying a radical, a square root box like this. Let me just put that down as a reminder. This is called a radical box or a square root, a root box. So that's what I mean when I say radicals. It's the square root box. Just keep that in mind. So how do we start simplifying these guys? We start with the factor tree. You take whatever number's inside there. In this case, 20. So I'm doing some side work to break down 20 into all the smaller numbers that multiply to make it. So 20 is the same thing as 4 times 5. And then keep breaking those numbers down as far as you can. 4 can be broken down to 2 times 2. And then we stop at 2's because 2 can only be 2 times 1. And we're only interested in numbers that aren't like 1. If you did that, then it would just go on forever, right? Because it's always the number times 1. So we stop at the prime numbers like 2, 3, 5, 7. 5 also we're done because it's only 5 times 1. There's no other multiplications that make up 5 for whole numbers. So we're done. So we've rewritten 20 as 2 times 5. And now we kind of go back to our actual problem of square root of 20. And I'm going to just switch out my 20 with 2 times 5. So here's our problem. And now I can substitute in what I just found that to be. Now, at this point, there's a couple different ways to do it, and there's a couple different ways to think about it. I guess I'd like to show you both just so that you have more options available for you to solve them. So here's the way I showed you yesterday, and I think on Monday. I'm going to write my 2 times 2 as 2 squared, or 2 to the second power, because that's what it means, right? A number times itself. And this whole unit is about exponents. So I'm going to convert that into exponent. And now we could write our square root. This whole problem could be rewritten as the 1/2 power. Recall from yesterday, we were going back and forth with our square roots and our fraction powers. So I can rewrite it this way. It's everything in the box, everything in the radical, 2 to the second times 5, but it's to the 1/2 power. Okay, now we can hand out our power. Inside powers all get multiplied to the outside power or exponent. The 5 doesn't have anything, so I'm going to give it a 1. That's okay. Anything to the first power is just itself. It's just the base. So we can do that when there's no power there. Now we multiply in our 1/2. What do we get? 2 to the 2 over 2, and then times 5 to the 1 over 2. Any questions right now, please? Comments about anything you've seen?
Wait, so do you always just put a 1 over the number? Like you see the 5, you just always put a 1 over the number.
Exactly.
And then just, okay.
Absolutely, Aaron. Yes, thanks for asking. Yeah. If we're doing exponents like we are here, then put a 1 over that number that doesn't have any exponent, like the 5. Absolutely. Why would we want to do that? Because I'm handing out this one I'm sorry, I lost my drawer. Here we go. Back at this stage, I'm going to distribute basically, right, my 1/2 power to all the inside powers. And if I don't put a 1 with that 5, I'm probably going to forget that the 5 should also be given that 1/2 power. That's why I'm pushing to use the 1 power. That's why, because frankly, I might forget. I'm not going to give the 5 the 1/2 power like it should have it. Everything in that parentheses gets it. And if I don't put the 1 there, I'll probably forget, or I could. So that's why I'm pushing that so much. So yes, short answer is yes. Always put the 1 there for anything that doesn't have it. Thank you for asking. Did that answer your question, Aaron? Yeah? Okay. Okay, so we're almost done here. It's looking pretty good. I see that I've got a 2 over 2 exponent, and that simplifies to just a 1. So this is just 2 to the 1 times 5 to the half. And why do we like this? Well, because we've got some of our original number, the 20, we've got some of that outside of the radical. We've got it doesn't have a fraction exponent anymore. So now our problem or our example can be turned back into radical form like it started. But notice that the 2, that's just 2 to the 1. So it's 2 times 5 to the half. And now we can turn the 1/2 power to the radical. So what do we have? We have 2 square root 5. So I guess one thing I should say is when we say simplify, when we're talking about radicals like square root of 20, um, what we want to do is get as much out of that box as possible. So we started with square root of 20, not a huge number, but it's bigger than 5, right? And now where we've ended is 2 times the square root of 5. So we've gotten as much out of that square root box as possible. Instead of a 20, it's a 5. And where did the rest go? Well, it's this 2. We've basically pulled out all the square root numbers we could, and it's outside now, and we've got only a 5 inside. Any other questions or comments on this example, please?
Why did we make the 2 to 2 1? 2 to the power 1 times
Good
5.
question. Good question.
Yep.
From this stage here down to the one below it, the 2 to the 2 over 2 power, sorry about all the 2's, folks, but see the exponent there, Braden? It was 2 over 2, right?
Yeah.
And then below that, I made it into a 1. Why can we do that? Because anything divided by itself turns into 1.
Oh, okay.
Is that okay? Do you remember
Yeah.
that rule now? Yeah. So anything like, and I'll do it off to the side, 100 over 100 turns into 1. X over X turns into 1. So we do use that shortcut trick a lot. If you see for these fraction exponent problems, we're looking for the number divided by itself for this express purpose. So that way we can get rid of the exponent essentially and turn it into just a 1.
Oh, okay. Wait, and I have one more question.
Please.
Why did for the 5 above, why do we put the 1/2 for the power?
Okay.
Where did that?
Yeah. So because, here, let me change my color real quick. So back here, we see that we converted from the radical box to the 1/2 power. Are you okay
Yeah.
with that step?
No, I don't understand how we got that.
How do we get that? Okay, so let me try to answer that question, and then we'll talk about where the 5 got the 1/2 from. So let me get a blank screen here. So I think the first time we talked about this concept, Braden, and everybody, was on Monday. It started here. We started talking about square roots, like for instance, the square root of 25, and we talked about that, and people were like, "Oh yeah, this means the number 5." And then I was saying that when we use fraction exponents, the 1/2 power, if you ever see that, that means square root of the base. Instead of 25 to the 1/2, we can write it as square root of 25.
Oh, okay.
And Okay, and then later in that lesson, and you were doing these with me yesterday, the more complex ones. Later in that lesson, we saw this business, a to the b over c. This is generic. That converts to, what is it? The c root of a to the b. Remember that?
Mm-hmm.
So we're basically just doing this, Braden. But when we use square roots, and I don't have a good answer for this, we don't usually put the little 2 out here. When we first learned about square roots, years ago, when you guys were younger, you first saw a square root, and they don't put the little 2 there. We just write the box, right? Um, so what's happening here is we're really just converting this. Let me show you again. Let's see. Our actual problem was 2 to the 2, back to the example, 2 to the 2 times 5. And what's happening is I'm converting this whole base to the 1/2 power using that ABC rule.
Oh, okay.
So this becomes 2 to the 2 times 5. That's our base, that whole multiplication, to the 1/2. Why can I do that? Because my root is 2. So that's where I got the whole 1/2 power from.
Mm-hmm.
Is that
Okay,
okay?
yeah, that makes more sense.
Okay. Yeah, and I'm sorry, I don't usually write the 2 out there. And frankly, neither would Admentum, and most classes wouldn't. But it is good we're talking about it, because if we have a square root box with no root here, folks, it's an assumed 2. So I should have said that. This is a 2 here whenever there's no number for the square root. And then we do write it for sure if it's a third root or a fourth root or a fifth root, right? We have to put the 3 or 4 or 5 there. But if you don't see a number, it's an assumed 2. Okay, now where did the 5 get the half root from? Well, or the half power? At this stage, back here, we've converted to the 1/2 power instead of the radical box, okay? And now it's like I'm going to distribute, I'm going to use the power to a power rule from last Thursday to, so to speak, hand out that 1/2 power to all the inside powers. And that's where the 5 got the 1/2 from. I'm handing out my 1/2 to the 2 to the 2, so we get this. And then I hand it out to the 5 to the 1, and we get 5 to the 1/2.
Okay, yeah, that makes more sense. Thank you.
Yeah, absolutely. Any other questions, concerns, please? So just in case I'm not being very clear, and I apologize if I'm not, this is our final answer down here, 2 root 5. No other comments? Let's look at another one, okay? I have another problem just like this one. Okay, I bumped it up a notch. We've got the square root of 60. Don't worry, it's a bigger number, but it's the same exact process. Folks, what was the first step we did for our last problem? First step is break down the 60 into smaller components, the numbers that multiply to make 60, using a factor tree. So I'm going to start that way again. I'm going to start dividing 60 by anything until we get to the bottom, and you can't break down, divide out numbers any further. Now, I've always been doing divide by 2 a lot, but the truth is we can divide by larger numbers. It'll still work out in the end. So why don't we divide by 10 here? Because it's 60 even, right? So I can divide that by 10. So 10 and 6. 10 times 6 makes 60. And that's how I'm finding these factor trees. Now break apart the 10. That's 2 times 5. And we're done there. 2 and 5 can't be broken down further. 6 can be broken down to 2 times 3. And I think that's it. Not too bad. So 60 turns into 2 times 2 times 3 times 5. Okay, so now that we've done our side work, we're going to just replace 60 with this business, 2 times 2 times 3 times 5. So back to the problem here in the middle. Okay, I told you in the last example we were going to do two ways, and forgive me, we didn't do the two ways. So quickly, I'm going to solve this the same way we did the last one, and then I do want to show you kind of a shortcut if you're feeling ready for a shortcut. Just so you understand, these are two ways to solve the same type of problem. So let's continue the same way as last time. We'll rewrite our 2 times 2 as 2 to the second. I should have been a little more creative, I guess. I didn't make a very different problem, did I? It's still 2 to the second. Anyways, let's convert it to fraction exponent now. Remember, square root of a base is the base to the 1/2 power. So I'm going to do that here. Now I imagine multiplying my 1/2 power to all the inner powers. Like Aaron mentioned last time, any numbers that don't have an exponent or a power, we should put a 1 there. So I'm going to do that now. 3 to the 1, 5 to the 1. Now hand out that 1/2. So what do we have? 2 to the 2 over 2 times 3 to the 1 over 2 times 5 to the 1 over 2. So just like last time, my 2 base here, well, the exponent is 2 over 2, which is 1. So this turns into just the number 2. 3 to the half, 5 to the half. Well, we can't simplify those any further. So what I'm going to do with those is just turn them right back into square roots. These are all being multiplied. So 2 times root 3 times root 5. One other thing I think came up yesterday, but I did a poor job, if I remember right, of explaining it. And this is it. And I want to talk about it again with you. Square root times another square root, well, those can be combined into one square root, like this. 2 is on the outside, so it's kind of untouchable. Okay, there's no other outside numbers to multiply 2 with. But my square root of 3 times square root of 5, well, I can multiply those together to be the square root of 3 times 5, 15. And here's our final answer. So the square root of 60 broke down, reduced, simplified to 2 root 15, 2 square root of 15. Questions, comments, concerns?
Wait, what happened to the half?
Good question. So remember in general, Aaron, remember 1/2 power means square root. I'll put it here at the top.
Okay.
X to the 1/2, and I'll circle this. It's just a side example. X to the 1/2 means square root of X. So we can use that principle back and forward, like both ways. And that's what I did in those last two steps, or last step was go 3 to the 1/2. I rewrote that as square root 3, and I did the same thing with the 5. Does that help, Aaron, or not really?
Yeah, I was just writing in my notes, so I'll remember.
Of course. Yeah, no problem. Now, I want to quickly show you guys a shortcut way. I'll do this in red, so hopefully it doesn't get too confusing. Let's make a note of it that we're just solving it a different way. And I'm not going to do it all from the beginning. Let's do it from right here. Okay, so I'm going to label this another way to solve it. Shortcut. So here's the deal. Back at this stage, we had 2 to the 2 times 3 times 5. What root are we taking right now? What's the number on the outside of this radical box? There's nothing, right? There's nothing written here. So Braden just brought this up a moment ago. Great question, Braden. If there's no number outside there, what do we treat it like? It's a 2, right? Just like how we add in our 1's exponents when there's nothing there. It's okay. I'm going to add in my 2 here just to kind of see this better. Even though there's no number, it is a square root. It is a 2. That's how we treat it. So the shortcut is, now that I'm looking at, okay, I'm doing a square root of this thing times this thing times this thing, these 3 items. Any of the items that match up with that root, the exponents that match up with that root. So this one is 2 to the 2, and I'm doing a second root, 2 root on the outside. So this means I can automatically bring out this base outside. 2. What's left? Square root of 3 times 5. 3 doesn't have a 2 exponent, so it's trapped inside. 5 doesn't have a 2 exponent, so it's trapped inside. Multiply those guys back together. 3 times 5 is 15. And we're done. And it's the same answer that we got over on the left. When we do it in the yellow way, the first way I showed you, I'm showing you all the steps using our actual legitimate power rules, exponent rules. This red way on the right, I'm kind of cutting some corners, but I am using those rules despite cutting corners. What's happening is I'm looking for powers like this one here, 2 to the second, right? That matches up with my root. And rooting cancels the squaring, or um, rooting cancels the exponents when they match. And that's why I'm just saying, okay, if I'm taking a square root of a square number, then I get to bring that outside, the 2, the base 2. And then 3 and 5, they don't have a square power, do they? So they're trapped inside. They don't get to simplify and come out. And we get the same answer either way. I think I've got another problem where we can use this shortcut and demonstrate that. Any questions? Please, comments. Okay, let's move on. I've got more examples actually. Let's keep going. Hopefully we get through them all. Here's another good one. I wanted to try, now that we've done 2 problems with square root simplifying, now we're doing a third root. Notice this. This is the third root of 54. Third root of 54. So this is a little different than the last 2 because we don't want groups of 2 items to simplify. We want groups of 3 items. So anytime we're simplifying radicals, even if it's a third root or a fourth root or a fifth root or anything, start with the factor tree. So I'm going to take my 54 and start breaking that down. If you don't recognize a bigger number to divide it by, just divide by 2 or 3 or 5 until you get something useful. So let's start with 2 here. So I divide 54 by 2 and I get 27. So that means 2 times 27 is 54. I'm done with the 2. 27 I do recognize as I can divide that by 9. I remember just happened to that 9 goes into 27. So what do we get there? 3. So 9 times 3. And then a 9, of course, is 3 times 3. Okay, so like the last 2 examples, I'm just rewriting 54 as 2 times 3 times 3 times 3. And as a power, as an exponent, let's just do that right now. 3 times 3 times 3, how many are there? Well, there's 3 of them, so that's the third power. So it's 2 times 3 to the third power. So we're going to swap out this expression for 54 back in our actual problem. Third root of 54. Here we go. 2 times 3 to the third. Okay, I hope this is not going to be damaging. I'm going to try doing the shortcut version. And if you like, we'll go back and then do it like the longer way, the full way afterwards. So I'm doing the third root this time, right? We're looking for groups of 3 items. Third root right here. Now look at the bases inside there. 2. Well, there's no exponent, right? So that's technically a 1. We can think about it as a 1. It's not a 3, is it? It's trapped inside. It stays. So I'm going to put my like answer below here. 2 is trapped inside. But for my next term, the 3, it has a 3 exponent, doesn't it? So that means a single 3 gets to come outside. This base is getting to come outside the box right here. So our answer is 3 times the third root of 2. I did the shortcut. Now I'm going to kind of back up to this stage where I left off in red and do it the other way. The long way this time, just so we see it all happening. Long way to solve. All right, so we left off here. Third root of 2 times 3 to the 3. So what I mean by the long way is I'm going to convert this to the power form instead of the radical. What does that look like? So the whole base is still there. But using our conversion rule, remember the A to the B over C? So I'm going to convert that to the 1 over 3 power. So what do we do next? Now I want to hand out that 1 over 3, that 1/3 power to the inside stuff. Give the 2 a 1 exponent. Cool. Now multiply the 1/3 to the other exponents we see. 2 to the 1/3 times 3 to the 3 over 3. I wish I would have realized that I was using the same base as the exponents. I didn't mean to make it confusing with all the 3's, so my bad. Let's keep going. So reduce the fractions you can. Can't deal with the 2, right? The 2 to the 1/3 can't change, so we're kind of stuck with that one. But 3 over 3 totally reduces to the number 1, so this is 3 to the first power, and that's the one that got outside of the radical. There's no more fraction exponent. So the 3 is outside because it's 3 to the 1. 2 to the 1/3 power, that's the one that's trapped inside. It can't reduce. Its power can't reduce. So I'm going to convert that back to a radical box for my answer, and we're done. So in yellow on the right, I've got our like traditional way. In the middle of the screen, we've got our kind of shortcut way, looking at which route we're taking and what are the powers we have inside. Questions, comments, please. It's 10:35, and I'd like to really quick stop and see thumbs with how people are feeling about these last 3 examples. Okay, Aaron, I see you. Thank you. Delaney, thank you for the feedback. Jayla, Noah, thank you too. Janessa, thank you. All right, that's all I'm seeing. All right, I appreciate the feedback. I hope other people are doing okay. Let's do a few more problems. Now I threw in one with more going on. Okay, we're gonna try this one out. Notice that the root's different this time. So let me read this out. This is the fourth root of x to the fourth, y to the sixth, z to the third. Okay, we're not breaking down a number this time because there's no whole numbers in here. It's just x's, y's, and z's. All right, and notice that because it's a fourth root, that means we're looking for like sets of 4. Any set of 4 items gets to, how should I say this? Gets to simplify and come outside the radical box. It gets to exit. Anything that doesn't reach 4 is going to be trapped inside, like we've seen with the last two problems. Okay, so let's do it this way. I'm going to start it below on the left in yellow. Fourth root of x to the fourth, y to the sixth, z to the third. I'm going to do this the traditional way, the long way first. How do we do it the long way? We're going to convert our fourth root to the 1 over 4 power right here. So remember, anything inside the box is your base. So I've got x to the fourth, y to the sixth, z to the third, and that's all to the 1 over 4. Okay, now what's our next step? We've got inside powers, we've got an outside power. What do we do with that? What
You
can we
gotta.
do?
Oh, sorry. I thought you were legit asking.
I am legit asking. I just can't shut up. Go for it.
Oh, yeah. You gotta times it into the to all the powers.
Beautiful,
No.
Braden. Absolutely correct. Thank you for answering. I'm going to do that now. Let's and do it with me. 1/4 times 4, so I've got x to the 4 over 4, y to the 6 over 4, and z to the 3 over 4. Fix that z a little bit. Okay, so folks, one at a time, one letter, one variable at a time. Let's go through the list, clean it up, reduce it if we can, and see what's left over. So x to the 4 over 4. Well, we've seen this a bunch of times today. The 4 over 4 turns into a 1. So we just have x to the 1. And you also know now that x to the 1 means just plain old x. So that'll be our final answer for x is just plain x, no exponent. What about y to the 6 over 4? Now, let's do this. I can't divide 6 over 4 and get a nice clean answer, but it can be reduced. So off to the side here, 6 over 4, if I reduced it by dividing top and bottom by 2, that's 3 over 2. And then z, I can't reduce 3 over 4, and I can't divide it. So I guess we're stuck with the z. It doesn't really change. It's just z to the 3 over 4. Okay, now, because we've got these different fractions, 3 halves, 3 fourths, we kind of have to continue dealing with the y and the z on their own. So let's regroup. What do we have? We've got x, y to the 3 halves, and z to the 3 fourths. So let's focus on that y to the 3 halves. So I'm going to do this kind of on the side, y to the 3 over 2. Now here's how I think we should try approaching this kind of problem. We've been converting back and forth all day this morning and this week from the radical to the power form, meaning the box to the 1/4 power, right? Back and forth. So with that in mind, I want to convert this 3 halves back to its radical box format. So recall from yesterday, we did a bunch of practice with this. Y to the 3 halves would become y to the square root, it'll become square root of y to the third. And recall from what I've been saying this morning, we don't write the square usually, the 2. It's just an assumed 2. So I'm going to clean this up finally by just calling it the square root of y to the third. That's my y portion. It's done. So I'm going to go, follow me back to the left now. So cleaning up the x, we'll just write it as x because it's x to the first power. My y, we just simplified that as square root of y to the third. My z, if we convert that, that becomes the fourth root of z to the third. Okay, now we can't combine the two square roots this time, the two roots. And the reason is they have different roots, different numbers. The y portion, that's a square root because there's no number there. So we treat it like it's a 2, remember? The z, though, is a fourth root. We can't mix these two together like we did a few problems ago when we multiplied the two square roots together. We can do that because they're both the same number, the same square root. Any questions? Concerns? Okay, no questions. All right, now I think I've got some slightly different problems to try. Same main topic, but slightly different than what the last four have been like. Let's see. Oh yeah, let's do this. So go ahead and copy this down. Notice that it's kind of a multiple choice. There's four answers at the bottom. All right, so we're asking which is equivalent, A, B, C, or D. Which one of those is equal to 10 root 5? Next week, when we get to our unit test, um, there are going to be a couple problems in the unit test like this. So I wanted to be ready starting now and start doing problems like this with you. Folks, basically, this is the same kind of work we've been doing, except it's backwards. It's kind of like they're giving you the solution. This is like our solution, 10 root 5, and they want us to work backwards to find out what it started as. So how can we go about this problem? Well, one way would be to solve all of these A, B, C, and D. But I don't want you to do that. I don't want you to do 4 problems in one if we can avoid it. So there's a way we can just work with 10 root 5 and work backwards. So let's do that. So I'm going to start with 10 root 5. And just to say it again, what we're trying to do is kind of build this back up. We're like undoing all the simplifying and figuring out which one of these A, B, C, D options is equal to 10 root 5. So start by converting the square root. We know that that is the 1/2 power, 5 to the 1/2 power. So I've got 10 times 5, and only 5 is the 1/2 power, right? The 10's outside, it's not getting that 1/2 power. Okay, this is a tricky step right here. So I'm going to do an asterisk here. Important. So what's going to happen next is a little different, and it's not obvious, okay? I want my 10 to have the same kind of exponent as my 5 does. I want it to have a 2, something over 2 exponent. So I'm going to make it 10 to the 2 over 2. You know what? Let me make this a little lower so we have some space. Sorry. Here we go. It's still important, but I'm just going to lower it down. Okay, so here we go. 10 to the 2 over 2 still times 5 to the 1 over 2. This is not an obvious thing that I would expect anyone to like have done on their own. It's a trick. Why can we do this? Why can I write 2 over 2 exponent for that 10 without like making stuff up? Like, why is this a legal move? Any ideas?
Because it ends up canceling out anyway, doesn't it?
Jayla, high five.
Yeah, thank
Yeah,
you.
2 over 2 is 1, right? So, like she said, it cancels out, and 10 is equal to 10 to the 2 over 2. I'm glad you saw that. So that's why we're allowed to do that. Now, I guess the question is, why would I want to? Well, I'm trying to build this original expression, 10 root 5, up and find out what's the big number inside the radical that broke down to 10 root 5. So I want to kind of get my 10 and my 5 together. And they can't get together until they both have a 1/2 power. So we're making it have a 1/2 power so that we can multiply that 10 and 5 together. Okay, so now we're going to do more backwards work. Usually we multiply in our power to a power, right? Outside powers multiply to inside. But we're going to undo that. Imagine going backwards here. So in step 4, watch this. Here's my 10 and my 5 still kind of hanging out. I'm going to put a parentheses around both of them. I'm going to pull out a 1/2 power. And now what's left over for exponents when I take away, when I undistribute that 1/2 power? The 10 still has a 2 because of the numerator. Back up top here, I'm putting dashes around it. That numerator 2 is still there, but I'm taking out the 1 over 2. And then 5 doesn't have anything. It has a 1. It just has a 1. We pulled out the 1/2 power. And now we can actually interact the 10 and the 5. But notice it's not just 10, is it? It's 10 squared. 100. Now I can multiply them. 100 times 5 is 500. And it's to the 1/2 power. And now you might see the answer. If you reconvert this back to square root box or radical box, it's the square root of 500. So it was option A. So this is the direct route. And if we can't do it this way, the only other way to solve it would be to solve all 4 of those options, A, B, C, D. And that's a lot of work. So I would like you guys to practice this approach, even though I know it's tricky. We had to do some tricksy stuff right here, step 3. And we kind of did tricksy stuff in step 4 when we pulled out that 1/2 power from both items. Questions, comments, concerns? Okay, let's do another one. I think I have another one like this. I hope we're ready to move on. I hope I'm not moving too fast. Let's move. Let's try it again. Which is equivalent to 5 root 3? So, and there's our options on the left, of course. So here's how we do it. Let's start with the expression they gave us. Start by turning the square root into power form. So 3 to the 1/2. So 5 times 3 to the 1/2. Okay, 5 doesn't have an exponent, so I'm going to give it a 2 over 2. So it matches up with that other one. Has the same like denominator. And now we're going to pull out the 1/2 from both of these. So 5 to the second times 3, and that's all to the 1/2 power. Just like last time. Now start simplifying inside the parentheses. So we've got 25 times 3 to the 1/2. Do the multiplication, that's 75. And now you see the answer. It is square root of 75. All right. No questions? I'm afraid I might be moving too fast, but you know what? I'm recording. Let's do a couple more examples before 11 comes across. All right. You know what? This almost looks like one of the last steps. in example 6. So this one says simplify 20 times 18 to the 1/2 power. So we want to take as much out. Okay, we like back to what I said in the beginning. We want to like get as much out of here as possible. So hopefully there's um, numbers in 20 and numbers in 18 that could be written as like something to the second. We want groups of 2 items. So that way when we multiply in our 1/2, they cancel out. We get like 2/2 exponent, and then it becomes a 1, and it's nice and clean. It's outside of the radical box. Okay, so how do we go about this business? Um, there's many ways. I am going to show you what we've been doing. So I want to rewrite 20 and I want to rewrite 18 as their prime factorizations. What I mean is do the factor tree and find the smaller numbers that make up 20 and make up 18. So even though this is a multiplication, folks, and it says 20 times 18, they've already separated some of that out for you. They could have given it to us as 360. That's 20 times 18. But they've kind of done the work for us already by dividing it as 20 times 18. So let's use that to our advantage, meaning don't multiply them together and make a bigger number. It's already smaller. So let's keep them smaller and find even smaller than these. 20 is 5 times 4. 4 is 2 times 2. So 20 is 2 times 2 times 5. So I'm going to write it as 2 squared times 5. Now for 18, this one is 6 times 3, and 6 is 2 times 3. So 18 is equal to 2 times 3 squared. Okay, so let's plug both of those expressions in for the 20 and the 18. So back in the middle here, let's see, 2, this is my 20. It was 2 to the second times 5. That's 20. And then 18 is 2 to the third to the second power. Now put in the rest of it, right? Parentheses to the 1/2. Now what do we do? Well, what do you see? We've got a bunch of terms. Some have powers. It's all to the 1/2. Let's multiply the 1/2 to all those inner powers. Let's throw a 1 in for 5 in the 2. Let's multiply our outside power to the inside powers. So 2 to the 2/2, 5 to the 1/2, the 1/2, 2 to the 1/2, and 3 to the 2/2. Okay, look for terms that have powers that could reduce and cancel. So the first one, definitely, and the last one, the 3. So this becomes a 2. I'm not going to write the 1. I'm just going to kind of skip that step because 2/2 is 1, right? And then 2 to the 1 is 2. So I'm going to just leave it cleaner. Now 5 to the 1/2 is still there. It's kind of stuck. 2 to the 1/2 is still there. And then times 3. Questions on how I did that, please? Okay, we're almost done with this one. Any outside numbers, or I should say any numbers without an exponent or without any powers, let's combine those. So the 2 and the 3, they can interact. They can get multiplied together. So that's 6. 2 times 3 is 6. And now I've got 5 to the half, 2 to the half. Well, those two can kind of get recombined. If you wanted to turn them back into radicals now, it would look like this. Root 5 times root 2. But those are the matching roots. They're both square roots, so we can multiply those together and get 6 root 10. And there's our final answer. Okay, I guess it's kind of late. So we didn't make it through 10 examples. We only made it through 7. I'm still going to give you the homework for today. Let's see which ones we can do. Oh, you know what? I think we can do 1 through 5. So here's our homework. It's kind of late, so go ahead and take a picture of this. We're doing the first 5 problems today. Go ahead and save 6 for tomorrow. We'll practice that type tomorrow. And frankly, 6 is from last week. So maybe I should make you do all 6 today. 6 was kind of a review homework problem because there's no fractions there. It's all from last week. So please, just a reminder, do these 6 problems on paper. When you're done, take a clear picture so I can see it, and then either email it to me or text me. If you're emailing it, make sure to label it Math 2 Exponent Homework number 2, because last week I'm calling that number 1. So that way I can differentiate between your different pictures. And if you text it to me, that's fine. Just write it at the top for me. So that way when I download it, I'll be able to easily keep track of it. So
And you want to put number 6 too, Josiah?
Yeah, you know what? I'm sorry for waffling. Let's try number 6. I forgot that that's just a review question anyway. So give it a shot. Tomorrow morning we'll go over these. But I do want to see you guys in your work and what you did get done on your own first. At least try it. There's a little more to review tomorrow. Thank you all for your time and for coming and your attention. Have a wonderful day.
Have a good day.
You too,
Bye,
Braden.
Josiah.
Bye, Jayla.
Bye.
Bye, Janessa. Thank you.